Hello everybody, welcome to this fourth video of Calculus of Variation. This is the fourth video we are having. So in this video what we will try to establish is we will try to establish the concept of closeness for functions, for two functions. Okay, this is why why we need it and things like that we'll discuss here in this video. So what we are going to do in calculus variation is, for example, you have this function. Suppose this is a function of n variables. Okay, and you have this functional. Functional is a function of, suppose, say one variable. So this is a function, and this is a functional, and this is a function of n variables. So you all of you must have this you must be knowing this, that when you study this maxima and minima problems of the functions. So, for example, you have a function of one variable f of x, and you want to find out at what point x this function has maximum and minimum values. You know how to do that. What you do is you equate the derivative of the function is equal to 0, and this equation will give you the possible values of x where the function can attain maxima or minima, where fx can have maximum or minimum values, right? So basically what you do is you find out the derivative of the function and you equate that equal to 0, and it means that your function has to be differentiable, then only obviously you can find the derivative. And if your function is differentiable, then it has to be continuous. What do you mean by a continuous function? You say that a function f of x is continuous at x is equal to a if that limit fx as x approaches a is f of a. So what does this mean? It means that when x is close to a, then fx should be close to f of a. Now here your x is a number, a is a number, and you know what do you mean by closeness of two numbers. And similarly fx is a number and f of a is a number. So again you know what is the meaning of the closeness of two numbers, right? So you basically this was a function of one variable, and so x is close to a. It means that x minus a, the norm of the distance, this distance between x and a should be small. Okay, this is a number and you know that this should be small. So and if you have a function of n variables, so you have 2 points, like your x will be actually x1 x2 xn, and your a will be actually a1 a2 an, and you say that these two numbers are small if the Euclidean distance between them, what is that? That is x1 minus a1 square plus x2 minus a2 square, and so on, xn minus an square whole square root. This is how the Euclidean distance between a and a is, x and a is defined. And you, by closeness of x and a, you mean that this Euclidean distance between x and a is small. So when you deal with functions, you know what is the meaning of smallness. You know what is the meaning of this closeness of two numbers x and a, whether they are one dimensional vectors or they are three dimensional or four dimensional. You have this concept of Euclidean distance, and you say that the two numbers or two vectors are close if the Euclidean distance is small. So now consider this functional. Now we you know we have this analogy. We will try to find out a condition such that this functional has a maximum or minimum value for a given function, right? So for that we need to the first thing required is the concept of closeness, right? So we need to have a concept of closeness. So this is the first thing we are going to do for finding this maximum and minimum of functionals. First we need to know how do you specify that two functions y1 and y2 are close. What do you mean by saying that two functions y1 and y2 are close? So for that we need some definitions and some theory we have to develop. Let's do that. Let me take a new window. Okay, so for that, for finding the what do you mean by the closeness of two spaces, two functions, we need to have something called normed linear space. we need to define a space called normed linear space. Most of you must be familiar with this space, but for the sake of completeness, we'll discuss what this is exactly. First of all, this is a linear space. What is a linear space? Linear space is also called a vector space. What is it? This is simply a non-empty set. You have a set non-empty set V with two operations associated with set. There are these are two operations. These are just the symbols. This plus actually doesn't denote that actually you are adding the numbers. It's just a symbol. So you have a set V which is non-empty for sure, and you have these two operations. One is denoted by plus and another is denoted by this dot sign. This plus operation is from V cross V to R if I am dealing with real vector spaces. So it means that you are taking two elements from V, first element from V, second element from V, and you are operating this function V. I'm sorry, this is not uh, R, this is V cross V to V. So basically, this plus is a binary operation on V. So what you are doing is you are taking two elements from V, you are applying this operator plus, and you are again getting an element of V, and this operator dot, this is from R cross V. So it means that you are taking an element from R is the set of real numbers, and you are taking an element from V, and this is giving you an element of V. Okay, so these are the two operations, and this set is non-empty. These two operations must satisfy certain property for this thing to make a linear space. This will be a linear space. A linear space is a non-empty set together with these two operations. The first operation is the binary operation on V, and second operation is from R cross V to V, which satisfy these properties. The first is, I'll write down the properties which this plus operator should satisfy. The first is it should be commutative. That is, for any two elements x and y in the space V, you should have x plus y is equal to y plus x. This should be true for all x and y in V. Second is it should be associative. This operation plus should be associative. It means that x plus y plus z should be equal to x plus y plus z. This should be true for all x, y, and z in V. What does that mean? It means that it should not matter whether you are first applying the operator on y and z, and then whatever you get, you apply that operator with x, or first you apply on x and y and then with z. The third is there must be an element. There must be an element in V. We denote that element with 0. Okay, this is just a notation such that if I'll operate any element of V with this 0, okay, I'll operate this operation plus with of any element with this 0, I should get that element back. Okay, because this is commutative, so it should be true for all x in V. This 0 is called 0 element. Okay, this is just a notation. This doesn't mean that this is 0 actually, that 0 the number. Okay. Okay, and the fourth one is for all x in V, there must exist an element y in V such that x plus y is equal to 0 is equal to y plus x. This is called additive identity. I'm sorry, this is not additive identity. This is additive inverse of x. Okay, so it means that this is that number which when you will operate with this plus sign to x, you'll get the zero element of the vector space. So generally we denote this should be true for all x in V, and generally we denote this y with minus x. This doesn't mean that if your x is 5 then this is minus 5. No, it's just a notation, right? These are the four properties with which this plus operator should satisfy. Now let us see what this dot operator should satisfy. Okay, that is the fifth property. The property is that there must exist an element in V. Uh, no, I'm sorry, it's not that property. we know that 1 already exists in R, right? We know that 1 is in R, 1 is a real number. So we must have 1 dot x is equal to x is equal to x dot 1 for all x in R. Okay. Actually, I should not write this because we have this one-sided. We are having this map from R cross V to V. So I'll just write it like this. This is the first property. We know that 1 is an element of R. So we should have 1 dot x is equal to x for all x in R, x in V. Okay. And the second property is that alpha plus beta dot with x should be alpha dot x plus beta dot x for all alpha beta in R and for all x in V. This is the sixth property. Seventh property is that your alpha dot x plus y should be alpha dot x plus alpha dot y for all alpha in R and for all x and y in V. And the eighth property is you can multiply two numbers in R. Obviously, this is the multiplication of alpha and beta. Alpha and beta are real numbers. Dot with any element of V should be alpha dot with beta dot x. This should be true for all alpha, beta in R and for all x in V. Okay. So if you have a non-empty set V together with these two operations plus and dot which satisfy all these properties, then you say that this is a linear space. Okay. Okay. So can we have an example of linear space? Yeah, it's very simple example of linear space. We can take this R2. R2, what is this? This is x comma y such that x and y are real numbers. This is our set. This is our V. Okay, and how I am applying the defining this plus and dot operation. I have two elements x1 y1 and x2 y2 of R2. I am defining this plus operation as x1 plus x2 y1 plus y2. This is how I am defining the plus operation. And how I am defining the dot operation, I take any element of V and any element of R. I am defining this dot operation as alpha x alpha y. Okay, this is simple multiplication of two real numbers. So you can check that these two operations, they satisfy all the 8 properties which I have listed. So this V R2 with that plus and dot is a vector space. Is a linear space or a vector space. It's up to you, whatever you want to call it. Linear space. Okay. Now, what is the normed linear space? I have this linear space. Suppose this is my linear space. Okay. After having this linear space, I'll define a map which I will denote by this from V to, okay, suppose R. We are talking about this uh, all the real things. This map should be such that I'm defining a map. Define this map such that we know there is a zero element in V. That norm of zero. This is called norm. This map is called norm. This map is called norm. Norm of zero. Norm of x. Any element should be. It can be zero if and only if that element is zero. Okay. Basically, we have this thing that norm of x is greater than equal to 0 and it is 0 if and only if that element is 0. That is the first property. Second property is that if I take any real number alpha and x, an element from V, then I know that alpha x is an element of V by the property of this dot operator. This dot is there. Then if I am looking at the norm of this number, then it should be equal to modulus of alpha. Alpha is a real number, so I can take the modulus and norm of x. And third property is triangular inequality, that norm of the sum of two numbers, sum is like that plus operator, that operator, okay, should be less than is equal to norm of x plus norm of y. This is the sum of two real numbers. This is a real number, this is a real number. So if I have a vector space, a linear space, together with this map from that space to R which satisfy these two properties, then I'll call this this thing V. This is my linear space, okay, and this is my norm. This is a normed linear space, okay. So this is a non-linear space. The elements here can be anything. They can be numbers, they can be vectors, they can be functions. And the distance between two elements, suppose f and g are two elements of V, then this norm f minus g, this thing, you know, this will be the distance. This will be treated as distance between f and g. Okay, what do you mean by this negative sign? Actually, what is this? F is an element of V. Okay, G is an element of V. I have shown you if there is a property of this linear space. If G is an element of V, then there exists an additive inverse. This does not mean that minus this G is minus G means negative of G. It is just an additive inverse. So I know that there is an additive inverse in V, and then I have f plus minus g. This is that operation, this operation. So this is an element of V which I am denoting by f minus g. Okay, so this f minus g is actually f plus this is operation minus of g. Minus of g is additive inverse of g. So this is an element of V, so I can take the norm, right? And this thing will act as a distance between f and g, okay. And by closeness of two functions, two elements of V, this normed linear space, we mean that this norm should be small, okay. We wanted to have a concept of closeness, so we have this concept of norm which will actually act like a distance between this two numbers f and g. The norm of f minus g will be the distance between f and g, okay. That can be used to generate the concept of closeness of functions. Let's take some examples to make these things clear. Okay, for example, I have this functional. Suppose I want to deal with this functional. Okay, so what type of here y is my input. We know that continuous functions are integrable, so all I need is that I should choose y such that this integral has a meaning, right? So I'm looking for continuous y for this. If I'm dealing with this particular functional, I want to look at a class of functions which are actually continuous on this interval ab, right? So I have this, I'll denote like this, c of ab, right? This is set of all continuous functions on the closed interval a to b, right? So this is my set. I can define an operation plus and dot like this. Plus is simple. For example, you know this x square plus 5 is a continuous function. X plus 2 is a continuous function. So plus is simply the addition of two functions. You know how to add two numbers. So this, two functions. So this is x square plus x plus 7. Okay. So this addition is normal addition of functions. And this dot is that I have a real number. For example, I have a real number 6. I have to define this operator. I have a function which is continuous on the interval a to b. This again, I'll take this function. So what is this? This is 6x square plus 30, right? So this is normal addition of functions. This is normal multiplication of a real number with a function. You can actually check that CAB with this plus operator and plus with this dot operation forms a linear space. Okay, you can check all the 8 properties are satisfied. So this is the linear space. Now what I'm doing is I'm defining a norm on this. For that, I should have a map from this set AB, CAB to R. How I'm defining that map is, I'm defining that for any element of this set are functions. For any element y, I'm defining a norm. I'll define it like this: 0 is equal to maximum of y of x. Okay, this yx, I can take the mod. Yx is a real number, x for a particular value of x. Okay, so first of all, how do I know that this thing is actually defined? So you must know this theorem that continuous function on a closed interval are bounded. Okay, so we know that this bound will actually exist. What is this? This is the bound of y of x, the value of y of x, right? And we know that yx is a continuous function. This is a set of all continuous functions. So we are taking an element from here. So for sure, y is a continuous function and ab is a closed interval. So, and we have this theorem that continuous functions on a closed interval are bounded. So we know that this bound actually exists. So we are not doing something which is superficial. Now you can check that this actually satisfy all the three properties of the norm. For norm, okay, you can check it. This is an exercise for you. So I have this normed linear space. So we have this CAB plus dot, this is our linear space with this norm that is defined like this is our normed linear space. We'll use NLS for that, normed linear space. Okay, so can we see what is the meaning of closeness here? Can you see? We suppose we have these two functions y1 and y2. Suppose y1 and y2 are two elements of this. What do we mean by the closeness of these functions? Let's see. In this space, in this non-linear space, what do we mean by the closeness of these two functions, y1 and y2? Okay. So, I have this function y. Suppose this is my function y1. Okay. And this is my a, this is my b. And suppose this this distance is epsilon, and I am drawing a function similar function like parallel line, and similarly suppose this is my epsilon. I'm again defining a, like I'm drawing a function like this. Okay, let me change the color. Actually this is my original function y1x. Okay, and this is, so if y2 is anywhere inside this strip, this strip is of width 2 epsilon. If y2 is anywhere inside this strip, then I'm sure that this y1 minus y2 norm is less than epsilon. Can you see that? Because this is how we are defining this. What is this? This is maximum of y1 minus y2 computed at x. Okay, y1x minus y2x computed at x on this interval, right? So if this is my function y1x and y2 is anywhere in this strip, for example, y1 can be here, y2 can be here, it can be like this. Okay, it can be any function inside the strip. If it is a function inside the strip, then I am damn sure that the distance between y1 and y2 is less than epsilon. Okay, okay, now let's see, let's look at some other functions, other non-linear spaces. Now let us look at the next non-linear spaces, next non-linear space. Suppose I want to deal with this functional. Okay, now if I want to deal with this functional, then I want my functions should be such that the first derivative should exist and it should be continuous. So that thing I'll denote with dab. D1 stands for first derivative, ab, this is set of functions which are having continuous first order derivatives. Okay, so for example, if I have this sine of x and my interval is from minus pi to pi, this function is in the set or not? Yes, sine x is continuous everywhere, differentiable many times, as it is actually infinitely differentiable function. So for sure it is differentiable for the first time. What is the derivative? That is minus cos x, and that is again continuous. So sin x is a function in this set. And how you define the plus and dot operations? Similarly, as we have defined for the CAB. Okay, simple addition of a plus operator means addition of functions, and this dot operation is multiplication of a real number with that function, right? So you can actually check that this set with these two operations forms a linear space. Now for norm linear space, I need to have a norm. So how I am defining the norm here? In this case, I'll define the norm, right? I'll write it like 1. This will be maximum of yx, where x is in the interval a to b, plus maximum of y dash x, where okay, x is in the interval a and b, right? Now can you see when we'll say that two functions are close? When we'll say that the norm between y1 and y2 is less than epsilon. Let's look at that. So basically, we want, suppose we have this we are saying that we have two functions y and z in this space dab, and I want to know when this norm y minus z norm is less than epsilon. What does that mean? It means that how this norm is defined. This is maximum of a less than x less than b, norm mod of yx minus zx, plus maximum of a less than z x less than b, y dash x minus z dash x. This is how this norm is defined, and I want this should be less than epsilon. Okay, now you know this is a positive quantity, and this is also a positive quantity, and you are saying that sum of two positive quantities is less than epsilon, then for sure each that positive quantity has to be less than epsilon. So it means that this maximum of a less than x less than b, y of x minus z of x, this has to be less than epsilon, and maximum of a less than x less than b, y dash x minus z dash x, this has to be less than epsilon. So basically, in this space we have two conditions for this functions to be closed. Okay, not only the functional values should be closed, their derivatives should also be closed. The values of their derivatives should also be closed in that interval for the functions to be closed in this particular space, for where the norm is defined like this. Okay, and similarly we can, we can define higher order, like we can define D and AB. What is this? This is the set of functions having nth order continuous derivative. Okay, and how do we define the norm in this case? We will define the norm, the plus and dot operations will be same, and you will define the norm as maximum of a less than x less than b, y of x, then y dash x, and so on, then nth derivative of x, like this. This is the norm. Okay, okay, so in the next video we'll see how we can use these normed linear spaces to establish the theory to find out the y's for which the functionals have maximum or minimum values. Thank you.